Good evening, everybody. How is everybody doing? I hope everybody is absolutely fantastic. Turn down that a bit. That's a sufficient enough volume. Good to see everybody here again for another Math 102. I hope everybody had a absolutely wonderful weekend. We're here to do another section here as part of the textbook. Yes. How's everybody today? How's everybody tonight? We'll get started here in a few minutes. We'll wait for a few more people to come on in, and then we'll go ahead and get started with the new material. Get that banged out of the way, and then we'll make it good. Just that simple. Not too bad, not too hard. I promise you that. Not too bad, not too hard. I can promise you that. Okay. Alrighty, good stuff. Okay. Wait for a little bit, and then we'll get moving. Check what I got here. Nice outside. It's nice outside. Ooh, excuse me. Yeah. Alright, terrible. Ain't the worst thing I've ever seen in my life. Whoa. Double dip. All right. Okay. Alright, we'll start here in just a couple more minutes here. Get a few more people in here, and then we'll get going here. And we will do a lecture, and then we will keep going with things to do. This I assure you. I see a few people here, so that's good. Should be just fine then. Okay. Alright. I guess we'll do some introductions here, ladies and gentlemen. and we will go ahead and get started. All right, let's get some started here with some new material. Hopefully, like I said, this will be a little bit shorter, and we will hopefully get this ball rolling. All right, let's do some intros and let's get going. All right. Okay, let's get started today. Welcome back. Welcome back to Tuesday. Hopefully you had a nice weekend. Alright, so for today, everybody, today we are going to be continuing to move forward here with the material. Now, just as a friendly reminder here, remember that we do have the chapters 5 through 7 homework and the chapters 5 through 7 test. Remember that is due on the 28th, okay? The 28th of October. That is next Thursday. So next Thursday by 11:59 on the 28th is when that will be due. So if you haven't worked on that just yet, I would suggest you do so. So that way you're caught up, and again, make sure you don't wait till the last minute. Otherwise, it usually doesn't end up well. Alright, so be sure to finish that up beforehand anyway. Okay, now, what we did, let's talk about what we did last time here in Chapter 7, because if you remember what we did here last time in Chapter 7, we talked about the normal distribution. That's kind of where we're picking up off here for today, okay, in section 8.1. By the way, we do have, this is the last quarter of the, last third, I should say, of the textbook. We'll have chapters 8, 9, 10, and 4 here to be. Chapter 4 will be our last chapter here. So, but we have a lot of pace here. We've got a lot of time with which to finish that material. So we should be good pretty much moving forward from this point on, in terms of doing a section or so a day. So, shouldn't be all that bad. Maybe we'll do 2 sections in a day on a couple of occasions, but nothing too crazy. Should give us plenty of time to review as well. Alright, but if you recall here, we talked about the normal distribution. We discussed that here at the end of Chapter 7. And once again, we're going to be discussing here stuff with the normal distribution once again. So essentially, if you remember, we did stuff with, say, normal CDF, and we did stuff with inverse norm on our calculators. We're going to once again use those 2 functions here in these problems here, just with a minor change, okay? That's essentially what we're doing here. And looking at it from a slightly different perspective, all right? So that is what we're going to be looking at here for today, using what we see here in Chapter 8. Let's go to the big board and see exactly what we're referring to here. And if you have questions along the way, please let me know. All right. Okay. Turn that down a switch. Okay, so let's talk about what we see here on the screen in section 8.1. Today we're going to be talking about a sampling distribution. So this is the part where we're starting to transition a little bit. So we're going to start transitioning away. We're going to start transitioning and saying, okay, we're not looking at the overall population now. Now we're actually looking at a sample. So remember, it's just like if we're asking people survey questions. We're asking 50, 100 people a survey question, say, do you like brand A? Whatever that, yes or no. And we say, okay, can we extrapolate the results from the small sample of people that we asked to the general population? And that's essentially what we're going to be doing here in subsequent chapters. And this is just like one of the first things that we're going to see here is like, all right, now we're given a sample size. It's going to be much smaller than the given population. All right, can we relate probabilities associated with it? Can we find percentiles associated with it? Or again, can we make conclusions on the population based from going the sample back to the population? Those are things that we are going to certainly do here and certainly look at. So the first thing that we're going to talk about here is a sampling distribution. So when we talk about the mean of a sampling distribution, if we're going to study the mean with the sampling distribution and relate it to the population mean, we're going to make the assumption here that the mean of the sampling distribution is equivalent to the population mean. So we're going to make the assumption, say, hey, all right, the mean of sampling distribution is the same as the population mean. Let's see what happens when we try it out if they're exactly the same. All right, so that's question 1. How do we find the mean of sampling distribution? It's the same as the population mean given to you in the problem. Now, the change that we're going to look at here specifically is going to be in number 2. And that's going to be the big difference here. And this is the part that I would suggest that you write down. Because the number 2 says, how do we find the standard deviation of a sampling distribution? So now we're looking over a smaller sample size here. And depending on the sample size is going to be exactly how we're going to look at the standard deviation. So the standard deviation here is going to be the population standard deviation divided by the square root of the sample size. That's what we have going on here. Okay, so move this down a little bit more. So, as you can see here by the notation works pretty much the same way. Again, here you have rho sub x bar, which is again the notation for the standard deviation for the sampling distribution. It equals the population standard deviation with rho divided by the square root of n. There you go. Simple enough. All right. So the question is, where are these two things going to fit in? All right. How are we going to use what we talked about here last week and be able to relate it to what we're discussing here today? Let's take a look at question 3. So question 3 says, what is the central limit theorem? And this is kind of like the big crux of what we're talking about here today. It says, regardless of the shape of the underlying population, as the sample increases, the sampling distribution becomes more and more approximately normal. So basically, here's what it's saying. It says, all right, the more people we ask, the more and more it will look like that bell-shaped curve, our ideal shape distribution. So that way we can go ahead and apply the things that we talked about here last time back in Chapter 7. So no matter what the population looks like, no matter how it's skewed, no matter which way it looks like, if you just increase that sample size, well, it means that it'll look more and more normal at the end of the day. It'll look like that bell-shaped curve that you're looking for. And this is going to provide us justification, essentially, to go ahead and be able to solve for probabilities using those same two functions that we discussed here last time, such as normal CDF and inverse norm. Okay, so that is what's on the agenda here for today. Okay, so let's take a good look here at a problem. All right, that's all right. We're gonna look at a problem here in the textbook. We're gonna do this together here, and let's see exactly how we can go ahead and do that. Okay, so we're going to do number 19 in the textbook. So let's do that here together. Talk about gestation period. All right, so let's read this off here together. So here we have, the length of human pregnancies is approximately normally distributed with a mean of 266 days and a standard deviation of 16 days. All right, now let's take a look here at letter B. Suppose a random sample of 20 pregnancies is obtained. All right. Actually, sorry, letter C. Suppose we have a random sample of 20 pregnancies, has a mean gestation period of 260 days or less. So we're given here a mean of 20 pregnancies. We're trying to find the probability of 260 or less days from those 20 pregnancies. Again, we're also given a mean here, okay, of 266, and our population standard deviation here in of a given study is given as 16. Okay? All right. So let's be able to answer this question here in this particular instance. Now, if you remember what we did here last week we went ahead and said, all right, if we're finding, 260 or less, or again, 260 more, whatever the case may be, remember that we're going to be using here the normal CDF function. Okay, since we're going to make the assumption here that, again, with the sample size, we're going to have it sufficiently large enough where it's going to be approximately normal. So, let's take a look here. Now, remember how normal CDF works. We got a second in vars. Okay, so to find it, once again, we got a second in vars. Go down to normal CDF. And don't forget here that we have 4 numbers that we need to enter in. Okay, so we have a lower, we have an upper, we have a mean, and we have a standard deviation. So hopefully this will jog your memory just a little bit from what we discussed here last time. Now, if we're talking about 260 days or less, let's talk about what numbers that we need to enter in here in order to find out this particular probability. So again, since we're talking about or less, we're going to first put in minus infinity on the calculator, at least represented, and that'll be minus 1 e to the 99. Now remember, to get this blocky letter E to show up in your calculator, you're going to go ahead and hit second and the comma key to have that blocky letter E show up on the calculator, followed by 99. And the upper here being 260. Then you have your mean here of 266, so that's not going to change. Again, I can justify that because we're going to make that assumption. Let's go back to the handout here for just a moment. The assumption here is that the mean, the sampling mean, is going to equal the sampling distribution mean will be equal to the population mean, so we'll be fine there. And now we have to change the standard deviation. So this is where the difference is going to lie here. We're going to change the sample standard deviation here. We'll take the population standard deviation and we'll divide that by the sample size. So for our last number that we'll have here, go ahead and put this all in. 260, 266. And then finally, we're going to have our standard deviation that we're given here, population standard deviation of 16, divided by the square root of 20, since that's our sample size here. Now, just be careful about how you enter that into the calculator. Let's go ahead and see here. If you have the new school calculator, it's pretty simple. If you have the old school calculator, just make sure you enter that in carefully. You have 16 divided by square root of 20. Okay, just like so. Go ahead and put that in. And we'll go ahead and figure out what this is. Alright, so here we get 0.0468. Okay, alright. And that's going to be our final answer. Now, just to be sure everybody's on the same page here, I would like everybody to type "got it" if you got this on your calculator. Make sure you entered in this correctly here. Type in "got it" in the chat if you got this on your calculator. Good. Again, just making sure everybody's got that down. Okay, Sanla's got it. Trolling's got it. Google's got it. Maritza's got it. Okay. Okay. Alright. Want to be sure everybody's on the up and up here for these. Okay. Alright, so that's the first question here. Any questions about this example? Any questions? Please type no in the chat if you do not have any questions, and that'll help me move on. No questions? Okay. Let's go ahead and do another example from the same question. Alright, so I'm going to change up the next one here. This was part C. We'll do letter D. I'll switch it around just a little bit. So what is the probability that a random sample of 50 pregnancies has a mean gestation period? And this time I'll change it here. We'll change, first of all, the sample size here. We'll look at 50 pregnancies, and we'll say, in this case here, the probability of 260 or more. Yeah, sure. Of course. Just tell me anytime you need me to turn it down because it's too loud. Please let me know. How's that, Sammy? Is that better? Okay, no problem. Like, I just leave it on and I just kind of forget about it, so apologies. So let's look at 260 or more here. All right. So we're going to go ahead and use Normalcdf here. All right. So we're going to go ahead and use Normalcdf here. So now the question is, what exactly are we going to enter into Normalcdf? What numbers are we going to enter in? Make that small adjustment there. What numbers are we going to enter into Normalcdf? Let's again, we have 4 numbers we got to enter into Normalcdf. But can you put that in chat here? What 4 numbers are we going to use for Normalcdf? Remember, you have a lower, you have an upper, you have a mean, and you have a standard deviation. So on Normalcdf, 260, 1e to the 99, 266, and 50 over the square root of 20. Oh, well, I'm going to agree with you on the first 3 numbers there. So 260, 1e to the 99 is true. 266, 100% correct. Now the standard deviation, remember the standard deviation here is equal to the standard deviation here divided by the square root of the sample size. I think you got a couple numbers there mixed up, Strolling. What would that last number be instead? And it's not 50 over the square root of 20. Back to our formula here. Up there. All right, there we go. All right, wait, minus 1e to the 99? No, Strolling, you were right for the first 3 numbers here. Just like I'm writing it on screen here for you, buddy. So, you got, the first 3 numbers are correct because it's 260 or more. I'm fine with that. Sanlav 50 is not correct. Remember, it says 260 or more. If I put 50, then that means 50 or more, but that's not what it says. It says 260 or more. So you start at the lower, which is 260, then go up to the positive infinity, which is 1e to the 99. And you guys almost have it. What's that last number supposed to be? Look at what you got here. You have the population standard deviation divided by the square root of the sample size. So what should that last number be, everybody? What should the standard deviation be? All right, there we go. That's correct. So our population standard deviation is 16. We're dividing it by the new sample size here, the square root of the sample size, which is 50. You guys are pretty close, but yeah, 16 over the square root of 50 is what we need here for that last number. So let's go ahead and plug that into the calculator here. So we'll put 260 here. Again, 1 second in the comma key to get that blocky letter E. 1e to the 99. Again, the calculator's version of positive infinity. 266. And then finally 16 divided by the square root of 50 for our adjusting for our new sample size. Good. All right, that's correct, Sanma. All right, so here we get 0.9960. All right. Type got it if you got this answer in your calculator. Make sure that everybody got this answer as well in the calculator. Okay. Good, good. All right, let's try another one. All right, let's try another one. I think obviously another one is in order. Okay. So the next one I want to show off here is going to be another type of problem that you could see on the homework. So again, I just want you to get another good look about how to approach problems that may look like this. So that'll be letter F here. So let's go ahead and read this one off here. Letter F. It says, what is the probability a random sample of size 15 will have a mean gestation period within 10 days of the mean? So we went ahead and we're changing the sample size from 50 to 15 All right, so we have 15 as our sample size. And we want to find the probability of the mean gestation between within 10 days and the mean. So can anybody tell me here, what does within 10 days of the mean mean? So within 10 days of the mean means what? Let's ask that question. What exactly does that mean? Within 10 days of the mean. The mean here, by the way, is 266, so don't forget about that. Okay. That's right, Strolling. Absolutely correct. All right, so within 10 days of the mean means plus or minus 10 days. So we have the mean right smack dab in the middle, which is 266 days. We'll go add and subtract 10 days from that particular value. And then we're going to get a range of days here of what they're asking us to look in between. So we'll do 266 plus or minus 10. We have the range here of 256 days to 276 days. So what we're really looking at here in this particular problem is the probability of between 256 and 276. Okay. So here in this case, we're going to go ahead and use once again Normalcdf. All right, let's go back to our calculator here. All right, the wrong number there. Sorry. Hang on a second. All right, there we go. Into Normalcdf. All right, so what numbers are we going to use here for this particular example? Numbers should we enter for this example? We have 256, 276, 266, and 16 divided by the square root of 15. Okay, that is correct. Very good. Nice job, Strolling. That is right. So 256 for our lower, 276 for our upper, 266 is our mean, and we have 16 here divided by the square root of our sample size here, which was 15. And we're just going to go ahead and enter that in, and, let's see what we get. Divided by the square root of 15, 1/5. We'll paste that in, see what we get. All right, so here we get 0.9845. All right, any questions about that last part there? We're going to do another example, but any questions about that one? All right. Hopefully pretty straightforward here. Okay. Let's take a look at another example then. Okay. And see something slightly a bit different, but that's fine. All right, so let's look at 25. Not the color I wanted. That's the color I wanted. Let's look at 25. Let's take a look at an oil change. All right, so let's read this off here. The shape of the distribution of the time required to get an oil change at a 10-minute oil change facility is unknown. However, records indicate that the mean time for an oil change is 11.4 minutes, and the standard deviation for an oil change time is 3.2 minutes. Okay, let's look at letter B. What is the probability that a random sample of 40 oil changes results in a sample mean time of less than 10 minutes? Right, so let's at least write down our information here. We are given a mean specifically, a mean here of 11.4. Our population standard deviation here is 3.2. And at least in letter B anyway, our sample size is 40 oil changes. We're trying to figure out the probability of 10 minutes or less. Well, 10 minutes or less. All right. So in this case, we'll go ahead and go back to the well here one more time. We'll use Normalcdf. What numbers are we going to use here in this case? What numbers do we use here for this case? I'm going to use Normalcdf here. Let's go back to our function here. Okay. All right. Let's see what we have here, Strolling. Normalcdf. Okay, that's right. And we have minus 1e to the 99. Good. 10. 11.4. 3.2 divided by the square root of 40. All right. That's correct. Very good. Nice. So let's put that in. Minus 1e to the 99. Put in 10. 11.4. And then we'll put in the last number here, 3.2. I'll move this over here. It's a little bit too far there. 3.2 divided by the square root of 40. All right. Let's go ahead and put in these numbers here. Again, we'll put in -1. Put it second and the comma key. E to the 99. We'll put the upper here as 10. So we want 10 minutes or less. We have 11.4. Finally, we'll clear that last one out. We'll do 3.2 divided by square root of 40. We'll paste it in. We'll go ahead and hit enter. All right, and we should get a final answer of 0.0028. All right, so 0.0028 is what we should get here in this instant. All right, so again, just like we did in the last few examples here, again, just making that adjustment here for our, again, sample size that we're factoring in at the end of the day. All right, very good. Very good. All right, questions about that one? Any questions? Again, if you have questions, please feel free to ask. Otherwise, if you don't have questions, please type no in the chat. Okay. As you see there, there's not a whole lot of difference between what we did in the last section and what we're doing in this section. Now, let's take a look at the last part here in this particular example. All right, so let's read this off here. It says, suppose that the manager agrees to pay each employee a $50 bonus if they meet a certain goal. On a typical Saturday, the oil change facility will perform 40 oil changes between 10 and 12. Treating this as a random sample, what mean oil change time would there be a 10% chance of being at or below? This will be the goal established by the manager. Okay, so in this particular instance, okay, this is where we reverse things around. So if you see a problem like this for part C, essentially we still have, in this case, we still have a sample size here, that being 40. So it's told us in the problem, but we're trying to find the 10th percentile of times here, according to this distribution. All right. So if we're trying to find the 10th percentile here, then we're going to go ahead and use our other friend here that we haven't used today. We're going to go ahead and use inverse norm. Now, just as a reminder from last week, go back to our calculator here for just a moment. With second in vars, we go down to inverse norm here. Remember that there are 3 numbers that you'll need to put in. You don't need to worry about if you have an old school or new school calculator. Everything will be defaulted here to the left if you have the old school calculator, and that's the one we're intending to use no matter what. So again, we are given a 10th percentile here, all right? So if we were to do this particular problem, we would first put in our numbers here. We could go ahead and put in 0.10 to put in our 10th percentile. And then we have our mean and standard deviation. Now again, our mean here is not going to change. It's still the same as we have from before, so 11.4. That doesn't change. What does change here, of course, is the standard deviation, because now we're given an actual sample size. So our standard deviation does need to be adjusted here, so it won't be like it was in the last section. So it takes 3.2 and we'll divide that by the square root of 40. So that adjustment still needs to be made regardless. All right. So taking that sample size into account, that has to be necessary. So let's put this in here. We got 11.4. And we got 3.2 divided by the square root of 40. And let's take a good look here at what we get for this final result. So here we have 7516, excuse me. So in order to hand out the $50, it should be 10.7516 minutes. All right. So that's what it should be there. 10.7516 minutes or below in order for the workers to get that extra $50 incentive. All right. Good stuff. All right. Any questions about that one? You can see there, we're just making one change here compared to the last section. All we're changing is that last number for standard deviation. That's it. That's all we're essentially doing. Now, I'll ask you, like I asked the first class here today. Would you guys like me to do another example, or are you guys pretty comfortable with knowing this stuff already? Would you like another example, or do you want me to want to do another example, or are you guys okay with this stuff? I'll leave it in your hands. Of course you can get one more if you ask. Yes, naturally. All right, let's do one more then, since Horitz asked. Not a big deal. Hey, look, if you ask, I'll do it. It's been like that the whole semester, so Just because I stopped doesn't mean that it's should be like that. No, you guys are always welcome to ask if you guys are not sure. Okay. All right. Let's do that next one then, and we'll quickly do this. This one's not so bad. So let's read this off here. All right. So time spent in the drive-through. The quality control manager of a Long John Silver's wants to analyze the length of time that spends at a drive-through window waiting for an order. It's determined that the mean time spent at the window is 59.3 seconds with a standard deviation of 13.1 seconds. The distribution of time at the window is skewed right. That doesn't really matter in this case. All right. So, letter B. We're going to look at letter B here. The quality control manager wishes to use a new delivery system designed to get cars through the drive-through system faster. A random sample of 40 cars results in a sample mean time spent at the window of 56.18 seconds. Okay. What is the probability of obtaining a sample mean of 56.18 seconds or less, assuming that the population mean is given to us as 59.3 seconds? Do you think that the new system is effective? All right. So, first and foremost, let's, at least for part B here, we need to write down a lot of pieces of information. Number one, we're given 40 cars here, so that's going to be our sample size. We're also given specifically the mean here is given to us as 59.3. Stated twice in the problem, but either way. And our standard deviation here, at least our population standard deviation, is given to us as 13.1. All right. So in this instance here, they want us to find the probability of getting 56.8 seconds or less. That's what we're trying to do here. So the probability of 56.8 or less. So we're going to go ahead and figure that out here within the context of the 40 cars that have been selected as being part of the sample. All right, so we're going to do the same thing here. We're going to do Normalcdf. Again, we want 56.8 here, so or less. So again, we're going to do minus 1e to the 99. 56.8. Got this over to the right here. Okay, and then we'll put in the mean here, which is 59.3. And then the standard deviation here, which is going to be 13.1 divided by the square root of the sample size, which is 40. And we'll enter that into the calculator first and foremost. Let's see what we get. Figure this out here. Second in vars. Go to Normalcdf. We'll do, again, minus 1e to the 99. Again, negative 1. Second and comma. Blocky letter E, 99. 56.8, 59.3 for our mean, and our standard deviation here, 13.1 divided by the square root of 40. So here we get a final answer of 0.1137. So now the other half of the question here, is it effective? That's what it says here. Is it effective? Now, one thing that we can say here based on this probability is it's not unusual because it's not below a 5% threshold, for example. But what we can say is it effective? Well, if your probability is 11% of the time of being below 56.8, seconds, then yeah, that's pretty effective. Okay, that's a significant difference between what you had before. So we could say, yes, it is effective. Not unusual, but yes, it's effective. Just because of the low, pretty low likelihood of it actually occurring. So that's why we can safely say, if it was like 40%, we could probably say, nah, it's not really that effective. It doesn't really change it that much. But 11% of the time we're at 56.8% or below with the current standard. It's pretty good. All right. Let's move on to letter C here. Okay. Move on to letter C here. Let's read this off here. It says, treat the next 50 cars that arrive as a simple random sample. So we're changing up our sample size here to be 50. All right, that's fine. There is a 15% chance the mean time will be at or below blank seconds. Okay, so there's a 15% chance that the mean time will be at or below blank seconds. So what do we want to do here in this instance? There's a 15% chance the mean time will be at or below blank seconds. So in this case, we're just trying to find the 15th percentile. Okay. We're going to use inverse norm for this. Okay. Since they want us to find that 15th percentile of times. So we're going to put 0.15 to reflect the 15th percentile. The mean here, which is 59.3. And the standard deviation here, which we have to adjust, is 13.1 divided by the square root of 50. We want to plug that in. So let's see what we get. Second in bars. Put an inverse norm. Put 0.15. 59.3 and 13.1 divided by square root of 50. And let's see what we get here. We'll paste that in. And let's see what we get here. So in this case here, we get 57.3799. All right, so 57.3799 is what we get here. So that's the 15th percentile. So essentially, if we fill in the blank here in the question, it says there's a 15% chance that the mean time will be at or below 57.3799 seconds. Okay, so with a sample size of 50 cars. All right, and that's how we can do both parts here for number 26. Any questions about that example there? Hopefully that cleared up anything that we just did. That clear up your questions there, and you got another look at another type of question. All right. Okay, very good, very good. So, that in a nutshell, ladies and gentlemen, is essentially the end of section 8.1. That's it. That's all you need to know. It's just that easy. All right. So, yeah, that's all I really honestly wanted to do today was just this particular section. And we actually buzzed through these examples pretty quick, so that was good. And that's all I essentially would like you to do today is just this first section here. Now, of course, your first priority besides this section is, of course, getting the stuff done for our chapters 5 through 7 for the homework and the tests, so be sure to go ahead and do that first and foremost. Okay, that will be your number one priority. And then if you finish that stuff, then go ahead and start working on chapter 8. Okay, so that's going to be the next thing in mind for what you want to do moving forward. Okay. All right. Any questions about anything? Hopefully, you guys got any questions about anything. Any questions at all? Nope. All right. Well, that works. Not a problem at all. All right. Well, if there are no questions here, all right, you guys get out early a little bit here today. I hope all of you have an absolutely wonderful night. What was the website you said we could use to get help on homework? Um, you, well, besides my math lab, you'd use, hang on. Oh yeah, that's Discord, my friend. So that's a web app. So, or again, you can also put it on your phone. So this is what Discord looks like. I'll put this on the screen here for it. So, this is Discord here. So if you need to ask me questions, you can feel free to do so. And there is a link to the Discord app should you need to use it. So there you go. And then we could get into a call and I can look at your screen and I can help you out if that needs to be necessary. All right. If you'd like to talk after class, Horitz, then we can certainly do that. That's not a problem. If you'd like to ask me questions, we can certainly do that. That's fine. Just make sure you're connected to Discord so we can get into a channel and then we can talk. Sure, Sanla, I certainly can. Give me a second here. Here you go, Sanla. See if I can shrink it down here for you. There, that's hopefully. No, that's a bit smaller, but hopefully that's a bit easier to read. I clicked on the invitation and nothing is happening. Oh. Yeah, it sometimes does that. Let me see. Where's the settings for this? No. Let me edit my invite link. Give me a second. It's the same invite link, but this should work now. Right now, or it's installing. See if that works. You're welcome, Sanla. Do you have the app on your phone, or do you have the app on do you have an account there, Strolling? Because if you have to have you could go through discord.gg. I'm clicking on the computer on the link there, right? Yeah, you have to sign up for Discord, so that way you get signed in. You have to sign up for Discord. It's absolutely free, of course. That's why I use it, because it's free. So, and it's free like sharing and stuff. So you have to first sign up for Discord. Just go to discord.gg, and then once you sign up for that, you can click on that link, and then I could have sworn you had an account before, but maybe I was wrong, Strolling. But anyway, maybe I'm imagining things. Any other questions before we head out here for today? I'll post the thing up here. If you're still having trouble, contact me via Discord, and just feel free to contact me via email. That's perfectly fine too. Nope. Okay. All right, ladies and gentlemen, I want to thank everybody for coming on ahead to the stream today. Horitz, is that your question down here, right here? I just want to be sure. Yes. Okay. I'll get to you in just a second here. I'll just log off, and we'll be good to go. All right, everybody. Thank you so much, everybody. We'll come back on Thursday, same time, same place. Horitz, I'll talk to you in just a second. Have yourself a wonderful night, everybody, and take care of yourselves. We will see you all later. Have a great one, everyone. And as always, everybody, stay safe, stay healthy, and most importantly, stay sane. Well, take care, everyone. We'll see you. All right, have a good one. Bye, everybody. Bye. Bye. Thanks, everybody. Take care.